My name is Tim Morris from the MRC Clinical Trials Unit at UCL, and this is a post-event recording of the first few slides because we didn't manage to record the first few slides during the actual event. So Lorna Orcott was chairing and introduced me, so just imagine that happening as you listen, and then I probably introduce myself afterwards, and then I'll get started. Now, what you'll see is at some point, I'm not sure if you can see my video on this recording now, but at some point I'll suddenly magically appear in a different building, and that's the actual live recording you'll be hearing there. So this talk is about trying to understand intuitively performance measures that we see in simulation studies. So what I'm going to do is kind of introduce simulation studies very briefly, but assume you have some familiarity with how they work. And I'm going to perform a very simple one with a couple of very silly methods as a way of kind of describing how we measure the performance of these methods and how we put together different measures to tell us what I hope you can kind of intuitively understand about which method is sensible and which one is silly in my example. I should say, just as a couple of acknowledgements, that, well, particularly for this talk, my thinking is very, very entangled, I suppose, with that of Ian White, who I've worked with on simulation stuff and other stuff for many years. And I'm going to show you later on something called zip plots, and I'm going to forget to say what the R package is that produces them, and it is called RSimSum. That's by Alessandro Gasparini, who has done an excellent job on that package. Okay, so to start off, here is my 4 easy steps to writing a statistical paper. There's a bit of clickbait for you. You won't believe number 3. So a statistician walks into a room just thinking about nothing much and suddenly has a brilliant idea, as statisticians constantly do. I'm sure if you're listening to this, you're familiar with this experience. They play around with their idea and start writing a paper about it. And this is the kind of, as they're bashing away at the keyboard, they're saying, well, look, we demonstrate with a simulation study that the proposed method has excellent performance. Step 3 involves an illustrative analysis using some real data set, and the method disappointingly gave exactly the same results as existing methods. And the 4th step is, of course, to recommend that everyone should use the method from now on. So let's think a bit about step 2 there. So the statistician did a simulation study and demonstrated excellent performance. So simulation studies are computer-based experiments where, or typically computer-based, that use pseudo-random sampling to understand the properties of statistical methods. So a very simple simulation study might be to somehow draw, as in randomly sample, some data set using either a model or some other procedure for producing data. The second step is to analyze the data with some method or other, perhaps more than one. And then the third step is to repeat the first 2 steps many, many times. Finally, then, we look at what's happened over these many times in terms of the summaries from these 2 steps. You know, you would have had some kind of possibly an estimate, possibly an estimated standard error, possibly a confidence interval, degrees of freedom, things like this that that we then get to evaluate what happens on average. So I'm going to do that. I'm going to set up a very simple simulation study. So I'm going to draw Y from a normal distribution with mean 1, variance 1. And I'm going to have two different data generating mechanisms. In the first one, I've got a sample size of 20, and in the second, I have a sample size of 50. And the thing we're interested in estimating, our estimand, is the expectation of y. So I'm denoting our estimand with theta. Now I have three methods of analysis. The first, kind of method A, estimates theta as theta hat A, or that's the estimator, is simply the sample mean. The next method, theta hat B, the estimator, is the sample mean times 0.9. Okay, so everything is going to just be a little bit closer to 0. The third one is pretty weird. So you toss a fair coin, and if it turns up heads, then you use the sample mean times 0.9. If it comes up tails, you use the sample mean divided by 0.9. Okay, so hopefully it's obvious to you that for this very simple setup, method A is sensible, method B is a bit weird, and method C is pretty weird. So I haven't said anything about what this toy simulation study is aiming to show, and essentially all I want to say is that it's a very convenient example to understand performance measures. So we're going to imagine that we don't know that our methods B and C are silly estimators, and we want to kind of understand their performance, to evaluate the performance, to kind of get a handle on their properties. So when I say performance, I'm talking today about kind of statistical performance in terms of statistical properties. But in practice, there are two computational performance measures that are really important. The first is speed, and the second is convergence. So speed is basically, you know, if you have one method that takes a tenth of a second to give you to spit out some result, and another that takes 3 weeks, then that is a pretty important difference. So you might be willing to accept poorer performance in the first method if you're doing it 100 times. You don't want to have to wait 300 weeks to get your results. The second thing is convergence. So some methods, and I'm sure you can think of some, will fail to converge every now and then. And I guess that's an important thing if you want to understand, particularly for planning analyses, then you probably don't want to plan an analysis with a method that doesn't converge half the time. At least to me, that's fairly important. So I'm not just talking about, I'm not talking about these because they're fairly obvious and intuitive, and I do want to focus on the statistical bits, but I also just want to start with the caveat that those things are important. So I'm going to mainly focus, as I talk through the results and the performance of these methods, on the scenario where we have a sample size of 20, but I'll give you some results for 50 as well, because that's useful for understanding some of the performance measures. So the first one that's perhaps the most obvious is bias. And bias tells us how much the expectation of our estimator exceeds the true value of the estimand. Okay, so the expectation of that, say, theta hat A, how much that exceeds our true value, theta, which here was 1. So the mean, the expectation of this, of the y, is going to be 1. And when I say exceeds, bias can be positive or negative. So the expectation can exceed it by, you know, a positive amount or a negative amount. It's not an absolute bias that I'm talking about. So I'm going to go through this a few times with different performance measures, just a kind of graphical depiction. So I've run this simulation study that I described, and I ran it with 5,000 repetitions. But for the graphical depiction, I'm just going to show the first 50 reps. By the way, I say repetition. I know a lot of people say other things like replication particularly, but I find it slightly confusing in language, just because there is the whole thing of replication of a study, that idea. And so I prefer to use repetitions to denote the sort of just repeated running of a simulation procedure however many times. But I can't persuade anyone else to use it, apparently. Okay, so here are the first 50 repetitions, and the bias for theta hat A you can measure by simply averaging the distances between this vertical line, which is the true value of our estimand, and the average of the kind of horizontal distances. Now that was theta hat A. Now for theta hat B, that estimator, we can see that all of those points kind of shifted to the left a bit. And of course they would, because all we've done is take the original sample mean estimates and multiply them by 0.9. So now you can see that there's a kind of hint that there might be some bias. So on average, these points may not be equal to that true value of 1. Sorry, just to say, vertically, these points are kind of spaced out vertically according to repetition number. So the bottom one is the first rep, the top one is the 50th rep. And that's just to give you some kind of visual separation. And you can imagine, perhaps I should have drawn them, but you can imagine the lines going from those to that value of 1. And you can also imagine, to the average of these estimates, and then comparing that to 1. Here's our method C. So this was the one where we tossed a coin to decide whether to divide by 0.9 or multiply by 0.9. And we can see that, well, things are sometimes a bit more to the left, sometimes a bit more to the right. There's just a bit more variability. Possible hint that there might be a bit of upwards bias as well. Okay, so this is where I got up to for the pre-recorded talk. So hopefully now there will be a seamless switch over for you to see this slide and then listen to what I actually said on the day. I won't talk through all the formulas because I know what that's like in slides. But in terms of a definition, it's basically saying, is the expectation of our estimator minus the true value, that is the bias. And then we estimate that using the sample mean of the estimated thetas minus a constant. Now, an important thing here is that when we run a simulation study, as with any study that has a finite sample size, what we actually estimate is going to have some inherent uncertainty about it. So we've estimated a bias, but it may not be exactly 0, or it may not be exactly the true value. And so the Monte Carlo standard error is something we can compute from each performance measure that we look at. And so this is essentially quantifying the amount of variability we have in our estimated bias due to using a finite number of simulations. So to kind of explain that a bit more, if I ran this simulation study and then I said to each of you, you need to run this simulation study, but we all used different random numbers when we ran it on our computers, then we would all end up with slightly different estimates of bias. If we ran a simulation with billions of repetitions, then we would have very, very similar results, whereas if we ran 5 each, we would have possibly fairly different results. So Monte Carlo standard error is trying to quantify that kind of aspect. So for our simulation study, here's a kind of table of the biases that we've computed. And what you can see is that I've put the N of 20 results towards the top of the table and n of 50 towards the bottom. And we can see that method A seems to be pretty close to unbiased, and we know we've got theory that says it will be, whereas method B seems to be biased a bit downwards, and we know that it will be again because we've made it biased here by minus 0.1. Method C, which is the kind of random choice of whether I'll go up or down from the sample mean, is a bit less clear here. Okay, so that's our first performance measure and possibly the most obvious one. The next one is called the empirical standard error. And this one often takes a while to get your head around. Some people find it obvious, others don't. But this is really just about the repeated sampling variation of theta hat. So in a simulation study, we compute it as just the standard deviation of our theta hats across the repetitions. So I've computed 5,000 different estimates of the mean, and then I just look at the standard deviation of those estimates. That's what I call the empirical standard error. Now, you may ask, why do you call it the empirical standard error and not the empirical standard deviation? Well, I guess it's partly because we usually reserve standard deviation for kind of a description of data and standard error for a property of estimators. But the main reason here is because I'm going to connect it later to the actual standard error we estimate when we have just a single sample. I'll come back to that. Okay, so here's our empirical standard error. Here, the vertical line now is no longer the true value, it's the estimated, it's the average of the estimated values that we got. And so what we do is just calculate a standard deviation kind of against that. So it's just how variable are these points into these estimates of theta hat. Okay, so we can see here, I guess as a kind of visual, this is a bit of a hand wavy visual because actually the way we calculate this thing is by squaring these. But we can kind of see that these distances here are a certain amount, but then for our method B, we can see that the distances seem to be actually slightly smaller than for method A. I'm just going to flip between them a couple more times so you can see that. And then for method C, it looks like these lines are kind of a bit longer than for the other two. Okay, so with the empirical standard error, our aim is for it to be as small as possible. We would prefer a method that has a low empirical standard error than high. And its definition is that it's the root of the variance of theta hat, and we estimate that in a fairly straightforward way. That's a standard deviation. And I'm not going to go much into these Monte Carlo standard errors because I'll give you a reference where you can find them all at the end. I just wanted to labour the point that they are important. Okay, so here we go. We've now got our simulation study again, and here is our empirical standard errors. Now, what's interesting is we can see that our method A has 0.222 at least on the top row for n of 20, but method B, this one that was biased, has got a lower empirical standard error. And I just said that our aim is to have it as small as possible. So that low empirical standard error is presumably a good thing. I've highlighted it in blue again on the bottom half of the table, where it's again slightly lower than B. Method C has higher empirical standard error, and that's because it's doing that thing where it's randomly throwing points out to left or right of the sample mean. Now, it's important to understand that empirical standard error needs some caution in its interpretation when we've got one method that's biased and another that's not. So here, I guess it's fairly obvious that method B would have lower empirical standard error because we've sort of just shrunk the points a bit towards 0. And we could get an even lower empirical standard error if instead of multiplying theta hat A by 0.9, we multiplied it by 0.01. Because then you've suddenly got these very small points, but very close together. Horribly biased, but hey, you've got a low empirical standard error. So it's important to take care around that, not just to say, this is the most, this has the lowest empirical standard error, so that's the best method. Okay, so now let's go to our third performance measure, the mean squared error. So this is one that kind of brings together the first two concepts. And I guess part of the motivation for this is that sometimes people might be willing to trade a small amount of bias for a better reduction in variance or in the empirical standard error. So the idea that you've probably heard of bias variance trade-off. So I guess given this, would it be natural to somehow combine the two, to try to combine bias with empirical standard error? So this brings us to mean squared error. What this is doing now is, instead of where empirical standard error was kind of using the squared distances from the estimate, mean squared error is using squared distances from the truth. And in doing that, it's starting to combine bias with empirical standard error in a specific way. So there we have it for our first one, our method A, we've got that mean squared error. If I flick to method B, you can see that now those lines are a little bit longer than they were before. Those distances to the true value are getting a bit bigger. And for method C, we can see that again it's fairly high. Okay, so with mean squared error, again, we want it to be as small as possible. It's defined there as actually fairly similar to empirical standard error, except that instead of a sort of theta bar, it just has true theta there. And interestingly, what you can see if we do it for this simulation study is that method A was unbiased and method B had lower empirical standard error. But you can see that that has kind of cancelled out, at least with n of 20, when we think about the mean squared error. Now, if we go down to the second half of the table, you can see that actually method B now has worse mean squared error than method A. Now I'm going to pick up on this point, sort of illustrate that now, or in a moment at least. So just to expand a bit on what mean squared error means, well, you can think of it as approximately the bias squared plus the empirical standard error squared. And that's not exactly perfect because of the denominator when you actually can calculate mean squared error, but it's pretty close. So if you've got a large number of repetitions, or no, so yeah. Okay, so let's think about this thing of sample size. Now, it seems natural, and I've motivated mean squared error as a natural way to combine bias and empirical standard error. But actually, I think it's better to report those two separately than just say, oh, we'll just smush them together into mean squared error. So here's an example. So in this graph, I've got bias independent of sample size. So the blue method is unbiased and the red method is biased. So it's biased by 1. But the blue method is going to be a little bit imprecise and the red method is going to be more precise. Okay, so here are the empirical standard errors. Red method coming down, or for any value of the sample size, the empirical standard error is lower than the blue method. And that comes down in a sort of root n way. That's why it's that curve. Now, what happens when we look at mean squared error? So just to be absolutely clear, the blue method is always less biased and the red method is always more biased. Also, the blue method is always less precise and the red method is always more precise. Now, when we look at the, well, I'm doing the square root of the mean squared error. we can see something interesting happens, which is that the blue method's root mean squared error is basically the same as its empirical standard error, and that's because it's unbiased. Whereas the red method, because it's got bias as well, it comes down towards 1, but because there is bias that is always there, it kind of comes down and will never go below 1, whereas the blue method can go below 1. And so for a sample size of 20, you might say, oh, well, the red method's got better root mean squared error. Whereas at a sample size of 100, suddenly it's the blue method that has better root mean squared error. And so I guess the point of this is to say that if you're comparing methods in terms of mean squared error, then you need to vary the sample size. All right, so the things I've talked about just now are all just properties of the point estimate that you get from a method. But as well as that estimate that you get, that theta hat, lots of procedures, most procedures will output a standard error or some kind of description of its accuracy. But let's say we've got a standard error and we want to say, well, okay, how accurate is that estimate of the standard error? And I'm calling so I'm going to call this performance measure the average model standard error. And actually, because we calculate, we compare them on the variance scale, I should call it the root mean, the root mean squared model standard error, but that's a bit of a mouthful. So we'll just think of it as the average model standard error. So here's this kind of visual description. So for each repetition, we get an estimate of the standard error of theta. And so here are the first 50. And I've kind of anchored them to 0 to give a sort of description of their magnitude. And what we can see is that, so we're going to square these, average them and take the square root. And if we do that, we get this orange bar towards the bottom, which is about a bit over 0.2. Now below that, I've put the empirical standard error. And that's because the empirical standard error actually describes the kind of repeated sampling standard deviation of theta hat. Now that is exactly the thing that our model standard errors are trying to describe. So the idea that if I were to repeatedly run this experiment, how much would theta hat vary? Well, in a simulation study, we have repeatedly run the thing, and so we can just look at how much it varies. So these two things, a good model standard error is one where on average it targets the true value of the empirical standard error. So for our second estimator, we can see that the average model standard error is actually a little bit higher than the true empirical standard error. And for the third one, it's a fair bit lower. Okay, so the aim of our model standard error, I'll explain that in a moment. So with our model standard error, all we want is for it to be an accurate representation of the empirical standard error. Okay, so this is very much a frequentist idea, right? So the idea that if you were to do hypothetical repeated sampling, how much would my estimate, here my estimate of the mean, how much would it wobble around if I were to draw different samples? So that's the empirical, or that's what the standard error aims to describe. And so we only get that, we get to do that once, and that's kind of an inference that we make from a single sample. But in a simulation study, we literally do the repeated sampling, and so we get to see how much our theta actually wobbles around if we repeatedly do that. So I think for me, when I learned about this, which was probably early in my PhD, I think that was quite an aha moment to go, oh, okay, so that's how I can actually evaluate the standard errors that I get given by a model, is to say, well, okay, well, how much I can compare it to empirically what I get in a simulation study. Faye, is that okay? Feel free to interrupt if that's not clear or if you want to clarify.
Hi, thank you. Yeah, please could you just repeat it again? Sorry.
Yeah, sure. Okay, so I'll start with empirical standard error, which is the one that only uses, if you take a single point estimate, well, you might want to know how accurate is that? How much would it jump around if I were to have a different sample of data and apply my same method? And so that's about that point estimate. And in a simulation study, we just take a different sample of data and look at different point estimates which happen to pop out.
Mm-hmm.
So the empirical standard error is just describing how much those estimates actually vary as we repeatedly draw different data sets.
Yep.
So then the model standard error is looking at the thing that we get when we apply a single analysis. So if we analyze a data set, we estimate a mean and then a standard error, and that standard error happens to be, say, 0.2. Now, what we want that thing to do is to accurately describe the empirical standard error.
Mm-hmm.
And so what we're going to do is to say, well, on average, is it accurate? Is it giving us approximately the right description of the true empirical standard error?
Right, okay, that makes a lot more sense. I think I was muddling them up. So when you first introduced the empirical one, I think I was interpreting it as what you then described as the average model one. So
okay.
Thank you.
Yeah, that's all right. Thanks for the question. Okay, so here's the table of the model standard errors, and actually we see much of a muchness for these across the methods. But why is it? So they're basically all coming out about the same. And by the way, I haven't told you how I calculated these. I calculated them by for each method by using the distance from the estimate, the point estimate, rather than just the standard deviation of the data. So I calculated sort of distances of data points from the point estimate for my standard deviation of the data, and then scaled that by root 1 over n. Okay, so these things are all coming out fairly similar, but the reason this is interesting is because we know that their empirical standard errors were a little bit different. So what I'm doing there is kind of informally comparing my model standard errors to the empirical standard errors. So I guess it's nice to do that a little bit more formally, which is using a performance measure I call the relative error in model standard error. So essentially it's sort of looking at the ratio of model standard error to empirical standard error. Now, I don't have a way to visualize this, I'm afraid, but basically I'm dividing model standard error by empirical standard error, and then I want that to be on a percent scale and just kind of with the amount of error. Now what I can do, if I compare them, I can see that method A is pretty good. It's got a pretty low error in the model standard error, whereas method B is overestimating the standard error. So the actual model standard errors it's outputting each time are actually on average a bit higher than they should be. Method C has the opposite problem, where its standard errors are a bit lower than they should be. So this leads us nicely to coverage. So when we learn about confidence intervals, we learn the definition as a kind of proportion of intervals that would cover theta if we were hypothetically to do repeated sampling. So, you know, if I constructed intervals in this way, then 95% of such intervals would contain the true value theta. I'll give you a visual representation of that in a minute. Now, in simulation studies, because we're repeatedly drawing data, we can actually appraise this claim of 95% coverage by saying, well, actually, how many of those intervals do cover theta? And so what we can do is look at this. So we've got our true theta is 1, and and we can just say, does an interval actually cover it or does it not? And in red, I've depicted the intervals that did not cover, and in black, the ones that did cover. So here for the first 50 repetitions, we've got 3 that didn't cover, which means it's a 94% coverage. Because I've only done 50, we can't actually get 95% here. For method B, we've only got 2 intervals that don't cover. One is very close and one is pretty far, and then you've got all the black intervals. For method C, we've got lots of intervals that don't cover, so there are 7 there that are not covering. Okay, so what we want with coverage is we want to say that the true coverage is equal to what it claims. So 95% of intervals do cover true theta. And actually some people are happy with that being greater than it claims, and which is a fair thing to be happy with. So there we have our sort of definition and the way we estimate it, and all it is a sample proportion, right? So we've got the number of intervals that actually contain the true theta. Now I've multiplied this up by 100 to be a sort of percent coverage. And we can see for our methods that we've got pretty good coverage. So for 95% confidence intervals, we've got pretty good coverage for methods A and B when n is 20. And method C has slight undercoverage. So the bottom half of the table, we can see that method B starts to have slightly poor coverage and method C has worse coverage again. Now, this is a kind of plot for coverage called a zip plot, and these I should acknowledge Alessandro Gasparini, who created an R package for analysing simulation studies, which you should definitely use if you are analysing simulation studies. This is called a zip plot. So just to describe this, on the left-hand side we have our results for n of 20 and the right-hand side n of 50. At the top we have all of our intervals for method A, and at the bottom all of our intervals for method B. Now what I've done is to order those intervals according to kind of a Z statistic, if you were to calculate that against the true value of theta. And so you get the intervals that sort of cover most right at the bottom, the ones that are dead center, and then the ones that are not covering are at the top. And they're kind of ranked in such a way that you kind of see this unzipping at the top of the confidence intervals. Now, one way to think of this is kind of like a game of hoopla, right? So you throw a hoop and it either lands on a stick or it doesn't. It lands or misses. And when we think about coverage, it doesn't really matter. If it misses, it doesn't matter how far you missed by, or if it covers, then it doesn't matter how perfectly on top it was or not. Coverage is kind of just saying, well, did 95% of the time these hoops land on top of the stick? I hope hoopla is. I'm suddenly questioning whether hoopla is the actual name of that game. I think it is. Anyway, you get the idea. So I find these useful because what we can see is that for method B, it had good coverage with n of 20. Whereas with n of 50, the coverage started to sort of degrade a little bit. And you can see that's because on the left, we've got several intervals that are missing to the left. We know that method B is biased, and so it's sort of starting to miss a bit to the left. And that particularly happens with larger sample size. Now, this is because when you get low coverage, it's broadly, well, it's exactly for one of 2 reasons, or both. The first is because of bias. So if it's systematically aiming to the left of the stick, then you're going to miss more to the left than you would like. And the second is that your intervals are too narrow. So that's like, imagine you're throwing a hoop that's small, and so it's much harder to get it on the stick. And so as with mean squared error, coverage can depend on sample size. Let me show you that. On the left is a plot of bias along with sample size. And we've again got our blue method A, which is unbiased, and red method B, which is biased, has bias of 1. Our empirical standard error and also our model standard error actually is on the plot on the right. And again, we can see that our red method has lower empirical standard error, whatever the sample size. Now, assuming that empirical standard error, that we've got intervals that are kind of a decent width in terms of representing, in terms of the actual interval width. So if a method is unbiased, then the intervals would be the correct width. Then this is what we get. So the blue method, which is unbiased, gets perfect coverage, whereas the red method, which is biased, is getting worse and worse coverage as the sample size increases. And that's because, if you think about it, it's kind of like each interval is getting smaller and smaller as the sample size goes up, but it's zeroing in on the wrong value because there's bias. So it's like really, really accurately just missing in the same way. So a fair question to ask is, well, okay, if it's composed of bias and interval width, the actual coverage property, then could we decompose that? And so bias eliminated coverage was an idea I had that kind of attempts to do that. So is low coverage due to bias or poor interval width or both? And so one way to think about this is, say, suppose there was no bias, how much under coverage would we see? And so we can do this by simply saying, well, look, let's consider coverage for theta hat instead of for the true value theta. So how many of our intervals contain the average across our simulation repetitions? So this is exactly like coverage, except now we've replaced theta in the middle of these expressions with theta hat. Oh, sorry, theta bar, which is the average across all our repetitions. And that gives us some interesting results. So it shows us that if method B were not biased, then it would actually have high coverage. Before, the coverage was actually about right, about 95%, but it's actually now 97%. And we see the same thing up here for n of 50, sorry, down here for n of 50. And method C actually has slightly better, but fairly similar under coverage. But I think it's nice to see that. So the coverage that we had for method B that was getting worse as the sample size increased, we can now see, once we take away the bias, that the coverage would actually be slightly too high instead of slightly too low. Why is that? Well, it's because our empirical standard error, our model standard errors are too wide. So as well as having bias, we've got intervals that are slightly too wide. Okay, so that's kind of some of the main ones, but many of you will have done simulation studies where you looked at rejection fractions, which like things like type 1 error and power. And I'm not really going to cover those because I don't have any particularly useful visuals for them. And I guess in a way they seem a bit obvious. But what I will say is that, as with other performance measures, they're in a dance together. So if you have high type 1 error, where that is kind of the amount of time you might reject a certain hypothesis, or the number of repetitions that reject the hypothesis, given that it's or reject a null when it's actually true, you can get high type 1 error in the same way, which is very closely related to low coverage. When you have that, you can end up with high power as well, which is basically you're sort of buying that high power through having high type 1 error. And it's a very similar situation to when you reduce the empirical standard error by just chucking in some bias. So I'm coming to the end now, and I guess the thing I want to say as a kind of conclusion is, first of all, that the choice of your performance measure should relate to your aims of your simulation study. If you have good theory that says your method is unbiased or tells you about the bias of the method, you probably don't want to actually report bias from your simulation study. You might want to run the simulation and check that you see the bias, that you kind of confirm your theory and confirm the maths that you've done or someone else has done, but you probably don't want to report that. But the reason you're doing a simulation study, you do have a reason, and if you can't pin that to some performance measure, then perhaps it's not clear why you're doing a simulation study. Now, in a simulation study, I think that by and large, you want to have more than one performance measure. One alone may be fine if you're trying to show that a method breaks. So if you just want to say, oh, this method is useless, then you might be happy to just show that it's horribly biased and be done with it. If you're trying to look at when a method works, you need more than one. And as a starting point, I hate rules of thumb, but I'm going to give a starting point as start with bias, empirical standard error, and coverage. If you're looking at something that estimates, say, a parameter or is targeting some estimand, and then go from there. So I've used those in a couple of papers, and I think that's well, at least sometimes that's a good kind of trio that covers lots of the properties. And this is something that certainly in emails with Ian White, we've emailed so many times. There was an email I sent him in December, example number 64,000 of why we look at one more performance measure. We send each other emails all the time where we've looked at a simulation study and found some problem with it. And a lot of the time, the issues are to do with people not really looking at more than one performance measure and drawing sweeping conclusions based on that. Here's one example, which is, I shouldn't be talking about this one because I don't understand the area well enough. I'm not really in this area. But my understanding is, so last year, two papers appeared which were evaluating shrinkage methods in a kind of prediction models context. And both of these papers reached this interesting conclusion that actually shrinkage methods don't just globally improve the performance of models. And that seemed to be new. People seem to just be saying generally, oh yeah, well, look, your prediction models will be better if you use shrinkage. Now, here's my interpretation from reading these papers, which is that the idea is they were looking at the calibration slope as their kind of performance measure. So their estimand was the slope of the calibration slope in some external sample to the one in which the model was created. And what these papers highlighted for me was that people had failed to consider more than one performance measure. So they'd looked at something being able to reduce the bias in the calibration slope, but these penalization methods that did that, ironically, increased the variance of that calibration slope. And one of the key points is just that actually you can often end up by getting, for a given model, worse performance when you penalize, even if on average it's improved. Okay, so that's everything I had to say. So thank you very much for listening. We've got 10 minutes, I think, for discussions. And Svetlana, I've just seen your question. Yes, you are very welcome to the slides. I don't know what the best way to share those is. I don't know. I'll take Lorna and David's.
Yeah, I think if you can send them to us, because it'll go with the recording.
Great.
And then I think the RSS enable us to put it into the website there under the meeting session.
Lovely.
So hopefully it'll all be very obvious.
Good.
Thanks ever so much. That was great. I was going to ask if you could just do a crib sheet of all those little performance measures, just to see them side by side would be for me really helpful. But yeah.
So this paper at the end has a table of some of the bits. It doesn't have the kind of, it doesn't have the intuitive bits. It's got the kind of definition and calculation bit, which embarrassingly I go and look at every time I have to do a simulation study because I forget how you actually calculate them. What
a relief.
Yeah. But I probably should do that. That would be a good idea. Yeah, thanks.
I feel vaguely justified because I used to use root mean square error when I was many eons ago, back in the dinosaur time, for my PhD. So I sort of feel, oh well, somebody uses it sometimes. That's good.
I quite like it because you get to look at it on the same scale that your standard error is on.
Exactly. So. Yeah. Any other questions from anyone on the floor? We've got quite an audience here. Very gratifying.
Jacqueline Thompson has a question in the chat about Monte Carlo standard error. Shall I take that one?
Yeah, go on.
So, okay, so thanks. So that's a really good question because I think it's quite. It's kind of like possibly the best way to explain this is a kind of inception thing, right? So with a simulation, you've got different levels of data sets, and the lowest level is the data set that you actually simulate. So you generate a data set that mimics a real study. Okay, so you might do that like, well, I did it 5,000 times. Now, then at the next level, I've kind of got a data set which is my averages or my kind of summaries of those 5,000. And that might be, for example, the bias or the empirical standard error. Now, the key thing to remember here is that I could have simulated a different 5,000 studies. And so when I summarize those, I would get some different estimate of bias or empirical standard error. The Monte Carlo standard error is a very simple idea in that it's just the standard error of my bias. So if I were repeatedly to do this, how much would my bias move around? And kind of intuitively, you know, if you run a simulation study where you do 20 repetitions, then you're going to have high Monte Carlo standard error because it's like having, when you analyze it, it's like having a sample size of 20. I had 20 theta i's. Whereas if I do it for 100,000, then I'm going to have much lower Monte Carlo standard error because I've averaged over those 100,000 repetitions. So I'm probably much closer to the true bias than I was when I just ran 20. Is that okay? I mean, feel free to come in, Jacqueline, if you want to.
She's shy.
Sure. Okay.
But you don't seem to be using that to really assess what's going on too much, which I thought you would do more of.
Yeah, I did. So I didn't a lot in the slides. I'll go back a bit because I kind of was informally doing it, but I was, where's an example? So I guess with bias, I was informally thinking about the fact that I'm probably happy to say that bias of minus 0.097 is a real bias because the Monte Carlo standard error was very, very low. And so it's just not compatible with that method being unbiased. Whereas for method A, that Monte Carlo standard error is the same size as the estimated bias. So I'm pretty happy. That's pretty compatible with it being unbiased. But yeah, I didn't talk about that really. I was just kind of put it there because I'm always trying to get people to report it. And so I felt I should probably do that as well. Ooh, Bethan, good question. So Bethan asks, do you ever pre-specify what an important level of bias is? Yes, I mean, have I ever done it? Probably not. Have I seen other people do it? Probably not. Is it a good idea? Yeah, I think so. Because effectively, when you, okay, so let's say you're calculating how many repetitions do I want to run in my simulation study. I probably want to rule out certain biases. Ideally, what you'd want to say is, oh, this method is unbiased. But what we're going to do is rule out biases of certain magnitude. And so to do that, we're going to have to calculate the number of repetitions we would need to rule out bias of whatever, 0.001. And that's going to be through saying, well, assuming the bias is 0 and the empirical standard error is whatever, then how many repetitions would we need to rule out bias of a certain magnitude? So I think kind of people maybe don't explicitly do it, but implicitly do so when, well, in the very rare cases, they calculate a sample size for a simulation study. I have seen people do it more for coverage, where they want to rule out coverage of less than 93%, for example. And then they'll come up with, you know, some sample size that would let you rule that out if your true coverage is 95%. Great question.
Can I just ask a quick question?
Sure.
So, you know, it's quite a trivial question. When you're reporting bias, say you're taking an average over your 5,000 replications, what do you literally just call it bias? I remember when I was writing my thesis, and we had loads of sort of back and forth about whether we should refer to it as average bias or just bias, or...
That is a really good question. Yeah, so, yeah.
Because I noticed you've done it with the standard error, haven't you? The average model standard error, the empirical standard error.
Yeah. So this is an argument I've been involved with and heard a lot. And I think, so with bias in particular, because it's defined as an expectation, then bias is kind of inherently...
Exactly, yeah.
Don't have an average bias, you have a single bias.
No.
Whereas with the model standard errors, because you effectively have a, well, when I talked about relative error in model standard error, that was effectively like, how biased is it? But yeah, I mean, I think average bias is a pretty weird thing to say, unless a thing that I've heard epidemiologists say, which I could not disagree more with, is that bias is just whether your sample estimate actually matches exactly the true value. And surely we all laugh at that and say, well, of course, it's never going to exactly match, but we hope on average it's not sort of going always in one direction. But I've heard some people be very vocal about this, which strikes me as bizarre.
Yeah, I just remember a lot of people had very strong opinion on it being average bias, but then my examiners would tell me to take it out and just have bias in it. So I just wondered if there was a
I suspect that is due to kind of coming from different definitions of what bias is.
Yeah.
And so as long as you have that kind of, you know, where is it? If given this definition of bias, then bias is bias. It's not kind of an average bias.
Yeah.
But if you were using a different definition, then yeah, perhaps average bias would make sense.
Okay, thank you. That's great.
Great. Are there any other questions? Oh, yeah, I think those are all really useful. And thank you for explaining those other little bits and bobs that have come up through the questions as well, which has been good. So I think we should probably start to wind up. David, I don't think we've got any announcements, have we? Do you want to just confirm that?
No, nothing yet. No more talks planned as of yet, but we'll get on the ball and do something. But I think you wanted me to say, Lorna, that just to remind people that RSS conference is coming to Aberdeen next year on the 12th to 15th September. Well, hopefully coming to Aberdeen next year. We've got no more news about the organisation or the programme of that yet, obviously, but hopefully in the near future we will. I guess as the next conference gets closer, we'll have more details.
Yeah, I suppose that's why, because things are a little bit still uncertain as to whether we'll be allowed to get together. Hopefully you can all come to Aberdeen and it'll be sunny and warm and lovely.
Yeah. It's like today.
Go on our whiskey trail and all of that, you know. But yes, I think we've got some other talks that are sort of in the pipeline. They've just not been finalised, haven't they?
We've definitely identified some people. We haven't got dates yet, so
yeah. We'll certainly let you guys know as and when we get those finalised and stuff. So. But I think we've done quite well. We've had 3 talks this year, so you know I think we've done pretty well so far. So I really thank you ever so much, Tim. We've And thank you for responding so quickly. I sort of called you out of the blue, and you just jumped at it, which was super. So great treat.
Thank you very much for having me. It's been really nice to join you.
Yeah. Okay. So we're a little bit running over time, and yes, lots of little. Okay. And I'm really sorry not to see you in the flesh, but almost as good.
It's nice to see you anyway.
Yeah. Yeah. So David, you'll get in touch with Tim about the recording and the slides, and I would really like a clip sheet.
Yes, I will do.
And if you've got the T-shirt, then that would be good. Okay. Thanks ever so much, everybody, for joining, and we'll see you all again at some stage. Bye. Bye.
Take care. Bye-bye.